So today we're going to begin another important application of integrals, and this is usually called something like accumulation problems. And how it works is like this. So what we know so far is that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f, capital F, is an antiderivative of small f. All right? Or another way to say this is that capital F prime equals small f. All right, so what we're going to do is we're going to rewrite this a little bit and say, well, look, if f is an antiderivative of f, then little f is the derivative of big F. So let's write little f as though it were a derivative, since it is a derivative of big F. And let's get this little f, big F thing out of the way. So we'll call little f f prime, and then we can just call f of b and f of a f. Right? So now we don't have the confusion of the capital F and the small f, but we're saying the same thing. F is an antiderivative of f prime, because that's the meaning of antiderivative, is that f prime is the derivative of f. All right, so now we just do a little hokey rewrite, and what we get is f of b equals f of a plus the integral from a to b of f prime of x dx. All right, so this is an amazing formula that can do lots of things. So let's throw a little bit of names on it. This up here that we started with, which we concluded right at the end of before break, this is called the fundamental theorem of calculus. All right, and often abbreviated FTC, and often referred to as part 2, but not always part 2. So there are different ways to derive the fundamental theorem. I've seen some books call this one part 1 and the other one part 2. Your AP College Board world always calls this part 2 of the FTC, and the majority of textbooks call this part 2. But just so you're aware, the designation part 1, part 2 is not universal. All right, that's your fundamental theorem of calculus. Now, also, this form can be called the evaluation form because it allows us to evaluate an integral. All right, this is called the accumulation form, or it's sometimes called, that's also not universal, but it's common enough to warrant mentioning, the accumulation form of FTC part 2. All right, so that's what that's sometimes referred to as. All right, well, so what? What can you do with it? Well, I'll tell you what you can do with it. You can do problems like this: accumulation and net change. All right, and we've sort of foreshadowed these a little bit. I'm going to get us started on number 1. You're going to be assigned this. It only has 6 problems. Can't be too bad, right? All right, it has 6 problems. Number 1, we have snow. This winter with things snow. Snowfall is predicted to fall at a rate in inches per hour. Now, here's the thing about snow. It doesn't just like start snowing at a certain rate and then just stop. All right, so the rate of change of snow, if you think of, inches per hour of snowfall and time, the rate of snowfall starts out 0, gradually increases, reaches a peak, maybe it plateaus for a while, and then it's going to drop off gradually. So the amount of snow that falls, the total amount of snow, is, if you had a constant rate of snowfall, then the amount of snow that fell would be that constant rate times the total time. All right, but since we have a changing rate of snowfall, the total snow that falls is going to be the area under the curve. So the area under the curve will be total snowfall. All right, total snowfall. All right, so we're going to try and do this number 1. We have snow predicted to fall at a rate, and so one of the key things here is they give us a rate. So that's like the f prime in that formula that I just introduced. All right, so this is accumulation. Let's call this the accumulation worksheet to distinguish from the packet you're about to get. All right, number 1. Okay, so we have a rate of 3e to the negative 0.5t minus 3 squared. All right, that's the rate at which snow is falling at a given time. All right, so we're going to set up an integral with that in the next video.